Good morning, everybody. I'm glad you could join us today. Welcome back to the California Tire Workshop Series, Day 4. We had a strong turnout yesterday, and hopefully we can get more people into this session today. I know it's of distinct interest. My name is Kyle Pogue. I'm an Environmental Program Manager at CalRecycle, and I serve as the Tire Workshop Series Facilitator. This workshop series brings together industry leaders, government partners, and researchers to advance sustainable tire management in California. Over 4 two-session days, we've explored market trends, regulatory updates, and emerging environmental research. More on that today, while strengthening the partnership needed to support a more circular tire economy. Today, we're excited to present day 4 of our 4-day series. We'll begin today with environmental insights, where the rubber meets the environment, moderated by CalRecycle's Senior Waste Management Engineer and Supervisor, and one of my favorites of our Tire Research and Engineering Unit, Mustafa Bhutan. We'll then conclude the series with program funding and grants, accelerating progress in tire recycling, that will be moderated by Nick Amante, a manager in CalRecycle's Financial Resources Management branch. With that, I'll turn it over to our first moderator, Mustafa Bhutan. Take it away, Moose.
Thank you, Kyle. Hello, everyone. Welcome to the Tire Workshop series. Today's session is titled Environmental Insights, where tire rubber meets the environment. My name is Mustafa Bhutan. I'm a Senior Waste Management Engineer supervising CalRecycle's Tire Engineering and Research Unit. The session will highlight the environmental factors related to tire materials and share findings from recent research on tire drive aggregate, TDA, and rubberized asphalt concrete rack, along with overviews of upcoming studies and programs. We will have 3 presentations lined up today. The first presenter will be Dr. Eileen Cashman, Emeritus Professor of Environmental Research Engineering at California State Polytechnic University, Humboldt. And during the QA, she will be joined by Dr. Brad Finney from the same department and university. Dr. Cashman will share the results of a state of knowledge study to evaluate literature regarding the short and the long-term environmental. Will share. She will share the results of a state of knowledge study to evaluate literature regarding the short and the long-term environmental impacts of the use of TDA in civil engineering applications and waste tire crumb rubber in rack used for road surfaces. She will be followed by Dr. Kelly Grant, a research scientist with DTSC's Safer Consumer Products program. Dr. Grant will provide an update on the findings and the ongoing development of 6-PPD alternatives, as well as DTSC's tire-related initiatives. Then we will finish this session with a presentation from Dr. Chan Harvey, Director of UC Pavement Research Center and a Professor of Civil and Environmental Engineering at UC Davis. And he will be joined by Dr. Angel Mateos, a research professor at the University of California, Berkeley. They will co-present and share an update on their research on assessing the risk of 6-PPDQ and selected metals leaching from rubberized asphalt mixes. Before we get started, I just want to remind everyone that the QA portion will be at the end of the session. After everyone has presented, you could submit your questions anytime using the QA widget. With that, I will hand it over to Dr. Eileen Cashman to kick off the session. Dr. Cashman, please go ahead and take it over.
Thank you for the invitation and the kind introduction. Let's see. Am I all good on my screen there?
Yep, we see it. I'm going to spotlight you just a second here, Eileen.
Okay, thank you. So I'm pleased to present some information that I've been working on with my colleagues at the Environmental Resources Engineering program in the School of Engineering at Poly Humboldt. I'm Eileen Cashman, and I've been working with Dr. Brad Finney and a couple of our students, Sol Wright and Stephanie Barajas, within our program here. We're going to talk about a state of knowledge report that we have been working on that covers water quality related impacts for tire-derived aggregate, or TDA, as I will probably say for the rest of the presentation, and rubberized asphalt concrete, or RAC. Just a caveat here, we are just completing the state of knowledge report for the RAC information, and we'll give you a quick update, but the focus of this presentation will be largely on the TDA. So I think, as many of you are very familiar with, California generates nearly 60 million waste tires every year. These tires pose environmental risks due to stagnant water that can breed mosquitoes. They pose fire risks that could be difficult to extinguish. And CalRecycle's job is to identify and promote the responsible use of these waste streams. Tire-derived aggregate, which is mechanically shredded waste tires, you can see in this picture here, is one of these products. There has been lots of literature that quantifies the engineering properties of TDA, things like it's lighter than soil, it has high hydraulic conductivity and porosity, and it's very effective in uses like dampening vibrations under railroads and thermal insulation properties. Tire-derived aggregate has been primarily installed in unsaturated subsurface settings, like some of the examples you see here. And this is really important when we're talking about the environmental impacts of water quality from TDA installations. So here you see some of the installations in landfills, pile walls, embankment fills, or vibration damping. We also looked at some of the installations related to stormwater infiltration galleries, septic leach fields, and constructed wetlands in this project. So TDA contacts water through precipitation, runoff, and in some applications, constructed wetlands. In most cases, the TDA applications are above the water table and not saturated, except in cases like constructed wetlands where the placement is intentional below the water table. Water quality questions about TDA have been reopened as new contaminants continue to emerge. And so our question was, what does the existing literature say about TDA's effect on water quality? In this review, we have looked at greater than 120 journal articles and technical reports. They include greater than 40 primary research studies that span from the 1990s to 2025. We've grouped them into 5 general constituent groupings that include common water quality parameters, metals and inorganics, organic compounds, PAHs as a separate grouping, and emerging contaminants. Our studies types that we've seen span from laboratory leaching experiments to field monitoring of engineered treatment applications. The geography, we have seen projects and research studies that are in California, to the middle of the country in Minnesota and Indiana, to the East Coast in Virginia and Delaware, and several international locations. So to start with the constituent groupings, I'll just summarize what we found from this State of Knowledge report. In general, for common water quality parameters like pH, biochemical oxygen demand, chemical oxygen demand, solids, and nutrients, the effects of TDA on water are comparable to those that we see for conventional aggregate. The impacts are negligible, and if there are some short-term increases in the initial contact, field studies show that these concentrations decline to background levels relatively quickly over time. One caveat or one thing that's worth noting is that TDA has been shown to actively remove phosphorus and nitrogen from water in some stormwater and treatment applications. These applications have been reported across stormwater, septic, and landfill applications and have shown that the effluent for phosphorus can fall below the EPA eutrophication prevention threshold. This has been confirmed in multiple studies, and the hypothesis is that it's an iron-mediated precipitation that comes because there are some wires from the exposed steel belts in the TDA that support biofilm development on the TDA surfaces. We do need to see confirmation of these systems that would require field studies over a longer period of time. In terms of metals, the key metals that we see leaching from TDA are zinc, iron, and manganese. We see occasional exceedances of the secondary drinking water standard, which is a non-health-based standard. Laboratory studies show a decrease over time, and field concentrations also return to background concentrations within a short distance of the source. One key note here is that metals do leach at lower pH water quality conditions. So in most typical installations, which are natural waters or urban stormwater, the pH is near neutral, and this minimizes the release of these metals. So pH is an important control, but what we've seen in most typical installations is that the metals are undetected or present in negligible concentrations. Volatile organic compounds or semi-volatile organic compounds is a third category that we looked at. And what we found here was that the leachate from TDA was usually a non-detect beyond very short distances away from the TDA installations. The commonly detected VOCs are things like aniline, benzyl thiazole derivatives, benzene, methyl isobutyl ketones, and toluene. In general, the lab and the field findings that we reviewed support concentrations that are below regulatory limits. One caveat is that we see lab exceedances that show benzene concentrations above California's standard of 0.001 milligram per liter. As with the other constituents, you see a rapid initial release with TDA exposure to water and then a decline within the time after. There have been a few long-term field studies, and they are often non-detects beyond the TDA fill within the field. The thought is that the likely driver of the decline in the field is depletion of what's readily available on the material near the surface in terms of VOCs and SVOCs, and the microbial communities that can help to degrade these compounds. We separated out PAHs as a separate VOC because of the literature that existed on this particular compound. In general, again, we saw concentrations from TDA that stay below the 15 micrograms per liter, which is the aquatic life protection objective. Naphthalene is the most commonly detected PAH, but again, concentrations remain well below toxicity thresholds. The field studies are fairly limited. We only identified 5 field studies in the reviewed literature. And these 5 studies all show concentrations that are at least an order of magnitude below environmental concerns levels. So in summary, up until this point, the properly designed TDA installations really pose minimal risk for well-studied constituents, which are the constituents that I just talked about: common water quality parameters, nutrients, metals, PAHs, and volatile organic compounds. The question that has really been reshaping the conversation are emerging contaminants, and that is really what precipitated this particular review as well. The emerging contaminant that I think we're all most familiar with is 6-ppdq. This was identified in 2020 by some University of Washington researchers that showed that 6-ppdq, which is a transformation product of 6-ppd, an antioxidant additive to tires, it showed that the 6-ppdq is the agent responsible for some coho salmon die-off in urban runoff. An important framing for our review of this literature is that most of the research focuses on tire wear particles. So these are fine tire wear particles. We included this information in our review because it's the same parent compound as what we find in TDA. However, the environmental conditions between what's happening with tire wear particles, which are on the road and running off directly into stormwater, is different from a TDA installation. We found only one lab study, which was a study that Dr. Finney and I did a year and a half or 2 years or so ago. It's the only published lab study we could find, which looked at leaching of 6-ppdq from TDA. We did find concentrations that were quite high, exceeding 3,000 nanograms per liter, which is well above the toxicity threshold. Toxicity threshold, or the LC50, the lethal concentration 50 for coho salmon, is in the range of 41 to 95 nanograms per liter. So this lab leachate is quite elevated. And that's what we found in the lab leaching studies, which is just soaking the TDA in water and examining what the concentrations were. We did not find any published field studies that investigate 6-ppdq from actual TDA installations. Most of the field studies and lab studies, again, were done on tire wear particles. So because the environmental conditions are quite different, it's really hard to infer the TDA specific behavior directly from the tire wear particle research. And I'll just repeat this again. It's because TDA is typically installed underground, it's wrapped in a geotextile, it's covered with soil, it's not in direct contact with the runoff off the road, so it's a fundamentally different exposure. Some of the other emerging contaminants that we saw discussed in the literature include DPG, HMMM, and PFAs. These are all emerging contaminants where we saw field evidence of concentrations that exceed protective thresholds. All three of these had caveats that did not provide very conclusive information about their impact with TDA installations. DPG, is often detected in surface water, and we did see research that looked at toxicity from leachates, but it was never singled out as just DPG. It was always in a combined stormwater runoff or water sample, and so you could not identify the impacts of DPG in terms of the toxicity for aquatic species. We're still looking at standardized and analytical methods. They're still in development for HMMM, and the research we saw is that PFAs have been detected in TDA leachate, but these concentrations are very low, especially when compared to sites that have had firefighting activities or manufacturing sites. So it's likely a minor concern in typical TDA applications. 3 decades of testing of the toxicity characteristic leaching protocol have shown that TDA is not a hazardous waste. Reported concentrations of the constituents they test for are at least an order of magnitude below regulatory limits. And the TCLP testing is really like a worst case scenario. It's extraction the concentrations under leaching conditions. It does not simulate field conditions, and it would tend to overstate the inorganic concentrations relative to actual installations. So to summarize, the lab studies systematically overstate field risk because they don't replicate our installation conditions. There's no direct contact with the water. There's no surrounding soil that might serve to bind or transform the constituents. The residence times are relatively short, and the tests are like the TCLP that are designed for worst case extraction. One of the studies that was reported on 2 years ago, which Dr. Finney and I did, we did find that passive soil filtration, not solar filtration, soil filtration, can remove more than 99% of 6 ppdq from tire rubber leachate. So we found greater than 99% removal for between 9 inches to 18 inches of different soils that included compost and topsoil or sand and mixes. And we found that it would, even with influent concentrations as high as 6850 nanograms per liter, the effluent was reduced to less than the LC50. So this could be validation that could be carried on further. This was for tire rubber leachate. This was not in a field installation, and validation is needed for that. So the conclusions from our review, there's 4 conclusions. That when properly designed TDA applications are implemented, they pose minimal risk for the well-studied water quality parameters. And this does not include the emerging contaminants. And they may even provide some net environmental benefits, as in the case for nutrient removal in stormwater and wastewater treatment systems. The big caveat is we found substantial knowledge gaps remain for the emerging contaminants, including no published field studies for 6 ppdq or related compounds in TDA installations. And this is the most consequential gap that we found. And we would also say that lab tests alone are not sufficient for evaluating the site-specific decisions that you make with TDA installations. A couple of recommendations for areas to look into further. There are some design considerations. TDA installations that are in areas of neutral pH conditions and have adequate buffer distances are really well set up to be minimal risk. And you can do things like expand the buffers when conditions are acidic or anaerobic. We recommend more monitoring and establishing protocols for emerging contaminants. There are some gaps there in appropriate monitoring and sample collection protocols. We would recommend more research, especially on existing field studies of TDA installations that have been in place for 10 or more years. So developing standardized assessment protocols for these emerging contaminants and to validate the soil filtration effectiveness. And adapting these new findings as they emerge so that we can support the continued beneficial use of TDA as a sustainable material, responding to this evolving regulatory landscape and emerging contaminants. As I mentioned, a companion state of knowledge review is underway for rubberized hot mixed asphalt, RHMA, which is also referred to as RAC. This review is in progress. We are finishing it up in the next week or so. The scope is similar in that it's a review of the water quality impacts of waste tire crumb rubber, which is used in rubberized hot mix asphalt and used for pavement surfaces. It's important that this is a separate review because this exposure is very different. RHMA is exposed to direct precipitation and runoff, also has traffic abrasion and sunlight. And so these are fundamentally different exposures than the ones that characterize the TDA applications. As I mentioned, the review is underway. The same emerging contaminant questions apply, and the results will be shared once we have completed the review and CalRecycle has had a chance to review it. This is just a summary of what I've already said of the open research priorities. I want to thank my colleagues for the work on this project. I want to acknowledge that two of our colleagues are student researchers who have worked with us at Cal Poly Humboldt. And I want to thank CalRecycle for the funding and the invitation and organization of this conference. Thank you.
Thank you so much, Dr. Cashman, for that great presentation. I would like to remind everyone that the Q&A portion will be at the end of the session. You can submit them using the Q&A widget if you have any questions. And with that, I'll turn it over to Dr. Kelly Grant. Dr. Kelly Grant, please take it over.
Try that again. Hi there. Thanks for the introduction, Mustafa, and thanks for Dr. Cashman for really setting me up on my presentation. I think she really outlined the importance of getting some of these emerging contaminants out of tires so that they can be reused in beneficial ways. And so today I'm going to talk about DTSC's activities to promote and encourage the use of safer alternatives to 6-ppd in tires. And I apologize, there's a bit of false advertising in my title. When I submitted my title, I was hoping I would have time to talk about zinc in tires, which is our other project, but I don't think I'm going to have enough time for that today. So today I'm going to review some of the science of 6-ppd quinone or 6-ppdQ. I'm going to provide an overview of the Safer Consumer Products Program or SCP and our alternatives analysis process. I'll discuss the results of the preliminary alternatives analyses for 6-ppd, present some new information on alternatives, and discuss the timeline for reformulating tires. So as a quick background, in late 2020, some researchers in Washington State identified the tire-derived chemical 6-ppd quinone as the causative agent of urban runoff mortality syndrome, or ERMS, in coho salmon. And ERMS was initially associated with mass die-offs of pre-spawn adult coho in Washington. And you can see that here in this image of this female that died full of eggs prior to spawning. Now, scientists subsequently showed that coho are sensitive to 6-ppd quinone at other life stages as well. But more recently, Ed Kaloje's lab has shown that the urban runoff mortality syndrome does occur in juvenile coho in creeks. Now, the LC50, or the concentration that's lethal to 50% of the test subjects, ranges from 41 nanograms to 95 nanograms per liter. So the lower the number, the more toxic the chemical is. And to put that in perspective, 41 nanograms per liter is just 41 parts per trillion, or roughly 2 drops in an Olympic-sized swimming pool. And in the next slide, I'll put that those concentrations into context based on what's found in the environment. So this graph shows detections of 6-ppd quinone in creeks and streams. And the red dashed line shows the 95 nanogram per liter LC50. And that's the LC50 for older fish. And each dot represents a detection of 6-ppd quinone. And so you can see how many of these samples, oops, I lost my cursor here, how many of those samples from San Francisco were exceeded or were close to that LC50. Now think about if they drop this line to that 41 nanogram per liter LC50 for the younger fish. And the level of toxicity and the level of lethality really increases. So we've known about 6-ppd quinones toxicity to brook trout, lake trout, rainbow trout for quite a while. But I want to highlight some newish data from USGS. So Shankar's data indicates that coastal cutthroat trout also show extreme toxicity to 6-ppd quinone. In fact, toxicity levels for the youngest fish actually overlap with coho. So it's important to point out that no toxicity is seen in other salmon or trout, such as Chinook or Atlantic salmons. There's been a dozen or so other fish species tested, and they also don't show acute toxicity. And the situation is similar with invertebrates. So it does seem to be a very specific toxicant, species-specific toxicant, I should say. And there have been some recent studies on some lethal, sub-lethal effects on fish, but I don't have time to discuss those today. So I've been discussing 6-ppd quinone. However, it's not what's added to tires. Instead, 6-ppd is. And as Eileen mentioned, it serves as the primary anti-degradant in tires. It is specifically designed to protect tires by reacting with ozone and oxygen. So what happens with ozone is it actually breaks the chemical bonds of rubber and causes these cracks that hopefully you can see in that image. And you can see in rubber with 6-ppd that gets protected from that ozone damage. The problem is when 6-ppd reacts with ozone, it specifically produces 6-ppd quinone. Now, when this research came out, 6-ppd quinone, or 6-ppd, excuse me, had been used for decades. So there was very little research on alternatives to it. And so that kind of outlines our problem. You know, tires need to have an anti-degradant, as you can see here, yet we need to protect salmon and trout. And that's really where the Safer Consumer Products program comes in. Whoops, sorry, went one too far. The Safer Consumer Products Program, or SCP, is a regulatory program that tackles the challenge of hazardous chemicals in products. And our program was designed to be precautionary, where we don't have to wait to regulate until there's proof of harm. Instead, our criteria for regulation is the potential for exposure and potential for adverse impacts. Now, please bear in mind that our regulations are not bans. Instead, product manufacturers can comply with our regulations by choosing to complete an alternatives analysis. And the AA, which I typically abbreviate as AAs, those AAs carefully evaluate the health and environmental impacts of the regulated product and its alternatives, with the goal of identifying safer alternatives and preventing regrettable substitutes. So regrettable substitutes are those that have significant adverse health or environmental impacts at some point during the life cycle of tires. Now, obviously, for this audience, thinking about a potential adverse impact or regrettable substitute would be one that reduced the durability of tires, and that could result in the generation of more scrap tires. So our alternatives analysis process is built to try to prevent that. Another potential adverse impact would be increasing rolling resistance, and that could adversely impact fuel economy. And certainly the impetus for this regulation was thinking about chemical hazard. We want to protect coho. But in addition, we know that any alternative to 6-ppd will be widespread in the environment just because of the nature of tire and road wear particles. So any alternative must be assessed for a broad set of hazards, including both ecological and human health endpoints. So our regulations on 6-ppd in tires went into effect in October 2023. And so I want to give you a little bit of update on where we are in this process. 75 global tire manufacturers responded to our regulations by conducting a preliminary alternatives analysis. Now, the standard SEP-AA is conducted in 2 stages. And in the preliminary AA, manufacturers screen a wide range of alternatives and select several promising alternatives to be assessed in the final AA. In the final AA, manufacturers will thoroughly compare the impacts of 6-ppd and the selected alternatives, and then the manufacturers must determine whether an alternative is feasible. And first and foremost, that requires assessing the performance of the anti-degradant and the performance of the tire as a whole. So for tires, a key part of that is that they are safe to drive. Beyond that, the final AA must provide information on all the new chemicals in a tire and chemicals that have increased in concentration. Additionally, the tire manufacturers must provide a schedule and a plan for adopting and implementing their selected alternative. So the preliminary AAs were due in March 2024, and over 90% of the tire market is in compliance with our regulations. And in part, that's due to the U.S. Tire Manufacturers Association, or USTMA, consortium. So their consortium represents 36 companies, which include the largest tire manufacturers. Now, in regards to the final AA, we've received several extension requests, in part because of the stringency of the requirements that I outlined. So the preliminary AAs collectively yielded a list of potential alternatives. And I do want to emphasize that potential. These chemicals need further screening because it's unclear whether they have adequate performance or if they're safer. So many companies selected other PPDs, those are shown in bold. And these are chemicals that have a very similar structure to 6-ppd. And that similarity makes them the best candidates to be drop-in replacements for 6-ppd. Now, I want to point out that this list is now obsolete. Some chemicals have been ruled out, other chemicals have been added. For example, in their progress report, the USTMA consortium stated that they were screening an additional 24 chemicals. So this list is evolving, as is the information about the alternatives, including other PPDs, which I'll discuss on the next slide. So initial reports about 7-ppd and IPPD showed that they both form quinones, but data suggested that their quinones were about 100 times less toxic than 6-ppd quinone. And that those results held up when 7-ppd quinone was tested on coho. But Washington State and their USGS partners took a different approach. They ozonated the parent compounds, and this may better reflect environmental conditions. And when they tested those ozonated compounds on coho cells, the margin of toxicity decreased to just 2 times less toxic for IPPD and 10 times less toxic for 7-PPD. Now, the mechanisms for this are unclear. Other transformation products may form, or the yield of the quinone from the ozonation reaction might be higher than would be predicted from what we know about 6-PPD. In addition, ozonated 7-PPD was cytotoxic to Chinook cells, whereas 6-PPD quinone is not. The US EPA conducted some experiments on rainbow trout gill cells. And in these tests, they analyzed many cellular features or many features of the cell at the same time. And their results are able to capture sublethal disruptions in those cells. And their toxicity ranking indicated that 7-PPD quinone caused the most cellular disruptions, followed by 7,7-PD quinone, and so on. Collectively, these results raise cautionary flags about these other PPDs. So SEP is adding the class of PPDs, or what we formally call PPD derivatives, to the list of chemicals that we can regulate because of concerns for aquatic toxicity of the parent molecule itself and skin sensitization. So that was not the most optimistic picture about alternatives. What else is out there? Well, the discovery of 6-PPD quinone really sparked innovation among chemical manufacturers and tire manufacturers. And so last fall, there was a flurry of press releases heralding the development of several new alternatives. One from a company called Perpetuous uses amine functionalized graphene. And it's my understanding that they are actually road testing tires with that alternative, indicating they're quite far along in their R&D process. Several other companies are beginning to offer trial samples of alternative antidegradants as well. However, the companies are not reporting the chemical identity of those until all their patents are in place. Now, the R&D timeline is slow, and to allow time for needed innovation, we've extended the timeline of the AA process to October 1st, 2029. So given that, what is a reasonable time frame to expect 6-PPD to be removed from tires? We know we're still years away. The very first step in tire reformulation involves a variety of lab tests to see how the alternative protects against ozone and how it changes a variety of properties of the rubber, like its stretchiness and strength, and a whole lot more. Once the tire manufacturer identifies promising candidates, they'll make a small batch of sample tires for testing indoors on a drum. If they get promising results, they may move on to field testing. And this could involve testing on a track and testing on fleets to understand how the alternative tire performs over time. Estimates suggest this could take roughly 4 years. If the alternative is a new chemical, it will need to get approval through EPA's New Chemicals Program and be registered by the European Chemicals Agency. And these can be lengthy processes. The other black box is how quickly the alternative manufacturer would be able to ramp up production to scale for the vast quantities needed for the tire industry. In the worst case scenario, this could involve building new chemical plants. Now, certainly the chemical suppliers are doing their best to avoid that, if only for their own benefit. But that kind of uncertainty makes it very difficult to project when alternative tires will be on the road. So unfortunately, I can't offer any certainty about when reformulated tires will be on the road. But DTSC's regulation, along with dedicated scientists and commitments from industry, have sparked a major global effort to find safer alternatives and reduce the harm caused by 6-PPD in tires. And I do want to plug that we will be hosting an online alternatives forum in September or October. So please contact me for details if you're interested. And thank you for your time and attention.
Thank you so much, Dr. Grant. That was a very informative presentation. And it seems 6-PPD will be with us for a while, what I'm seeing there. So thank you so much. And just a quick reminder that the questions can be submitted at any time using the Q&A widget, and then we will answer it at the end of the presentation. With that, I will pass it over to Dr. John Harvey and Dr. Angel Mateos. Gentlemen, it's all yours.
Okay, thank you very much for the introduction, and thank you very much for the opportunity of presenting doing this presentation. We're going to be talking about the assessment of 6-PPD-Q pollution risk from rubberized asphalt mixes in California. We're going to do first a very brief introduction. And we're going to go very quickly about across the 6-PPD concerns, because I think that all of those concerns have been very clearly stated by Dr. Grant. Then we will be talking about how we use the recycled tire rubber in asphalt mixes and why there is some concern about the potential release of 6-PPD-Q from the rubberized asphalt mixes. Then we will talk for a moment about what we know so far, which is not a lot, but we know something about this topic. So we will be presenting some results from a study that was conducted recently at the University of Nevada, Reno. And then we will be presenting some order of magnitude calculations and the results of a previous study conducted at the University of California Pavement Research Center about the toxicity discharge from asphalt mixes. Finally, we'll be presenting a research study that has just started. That's a research study that the UCPRC, the University of California Pavement Research Center, will be conducting for CalRecycle. As I said, we're going to go very quickly through the 6-PPD concerns because they have been very clearly stated. One thing that I would like to mention is that the lethal concentration of 6-PPD-Q, those values that you can see in the literature, the value of 95 nanograms per liter, that was the original value reported by scientists at Washington State, or the other value that Dr. Grant presented, the 41 nanograms per liter that was reported that was developed in Canada, those refer to 24 hours exposure, right? It doesn't mean that the salmon can live here. It's just 24-hour exposure. That means that 50% of the fishes will die. So there is another value that has been proposed as a screening value by the US EPA, which is 11 nanograms per liter, and that could be applicable to the receiving water, to the surface water. That is the concentration that you should have, the maximum concentration that you should have in your receiving water, and cannot be exceeded more than 1 hour every 3 years if you want to have a healthy environment for the coho salmon. Again, that's just an initial value, is not mandatory, but it gives you an idea of this challenge. It's just 11 nanograms per liter. The other thing that I would like to emphasize is that we're talking here, we have like two different types of waters. One is the stormwater runoff, that is the water as it comes out of the highway. Okay, that water is expected to have a very high concentration of 6-PPD-Q because it's just coming out of the highway. But that is not where the fishes will live, right? Then the water will go to the receiving waters, and in the receiving water, the concentration is going to be lower than what you can expect in the runoff water. And there are two main reasons for that. One is the degradation of the 6-PPD-Q. The 6-PPD-Q will live in the order of hours or a few days, so that's why the 6 ppdq will be disappearing versus time. And more important than that, we have the dilution effect. So again, two different types of waters. One is the runoff water that will have a very high concentration, and then the surface water that should not have that high concentration. Then we use rubber in asphalt mixes, right? That's very common in California. In fact, the California Department of Transportation has the obligation to use rubber. There is a legislation that forces the California Department of Transportation to use rubber in the asphalt mixes. And the other reason why rubber is used in the asphalt mixes is because the rubber provides a very high cracking resistant properties to the asphalt mix. So it's very convenient from the environmental point of view and from the performance point of view, the use of the rubber in asphalt mixes. In the year 2024, around 40% of the asphalt mixes that were placed by Caltrans, the California Department of Transportation, had rubber. And because of that, Caltrans was able to recycle in the order of 2 million tires. In the total of California, in the same year, in 2024, around 6 million tires were recycled into asphalt mixes. That's not huge, but at least it's in the order of 10% of the waste tires that are produced in California every year. And then it's important also to mention that the practical totality of the asphalt mixes with rubber in California belong to any of these two types, the rubberized hot mix asphalt gap graded or the rubberized hot mix asphalt open graded. In the two cases, what these two mixes have in common is that we introduce the rubber, and by the rubber I mean this is crumb rubber modifier. This is just the rubber as it is in the tires that have been crushed into fine grains, right? So that's rubber powder. This powder, it's not totally powder, but it's relatively small particles in the order of 2 millimeters or 0.1 inch and below that. This powder is introduced in the asphalt mix through a process that is called the wet process. So we don't really add the powder directly to the asphalt mix. Before doing that, we blend the rubber with asphalt and we produce something that is called the asphalt rubber binder. This is the product that you can see here. You can kind of see the grains from the rubber here, but again, it's very important to picture that we don't take the rubber and add it to the asphalt mix. We blend it with binder, we produce this asphalt rubber binder where the rubber particles have been coated with binder, and then that is what we use for mix fabrication. But still, there is a concern, and it's a logical concern, that because the asphalt mix has rubber, there is a possibility that the 6 ppd in the rubber will become 6 ppdq, and then that will be released into the water and then may create additional 6 ppdq contamination. That's a reasonable concern. The rubber may come, for example, from the surface, right? When you pave the asphalt mix, there is a thin layer of asphalt that is on the surface that will be removed by the traffic. So of course that particles that are removed may contain 6 ppdq, and again also because of the traffic effect, there will be some disintegration of the asphalt mix, so there will be particles, and then there will be cracking, so water can come through the asphalt mix. So again, there is thinking that the asphalt mixes could increase the 6 ppd contamination is a reasonable concern. We know something about this, right? There was a study, as far as we know, there's been just one study on this specific topic that was conducted at the University of Nevada, Reno, a few years ago. And what is the main conclusion from the study? I'm going to read it. It's here. You can read it here. Is that while the release of 6 ppdq from compacted rubberized asphalt mixes is minor, the mixtures can serve as sorbent for the tire-derived 6 ppdq. Let me just share with you these two plots. In the top plot, what you see is the concentration of 6 ppdq increasing versus time, and this is water where they have introduced asphalt mix. So you have asphalt mix, you soak your asphalt mix with water, and then you can see that the 6 ppdq contamination is increasing versus time. And again, this is clean water that has been covering the asphalt mix. it doesn't reach very high levels, right? We're talking, this is micrograms. So the threshold values that we were mentioning of 95 nanograms per liter would be 0.09. So again, there is a potential of 6 ppdq released from water, from the asphalt mixes. That's clear. But at the same time, and I want you to see this plot on the bottom, if instead of pouring clean water on top of the asphalt mix, you pour water that has 6 ppdq, and that's the typical case that you will see in the highways, because again, the water, the stone water in the highways will have 6 ppdq. What happens is the opposite. What happens is that the asphalt mix will be absorbing the 6 ppdq. So again, there is this trade-off where, yes, there is a possibility of minor 6 ppd contents releasing from the asphalt mix, but there is also the possibility that the asphalt mix will be cleaning the water because it will be absorbing the 6 ppdq in the stormwater runoff. So that's what we want to expand in this research, is what is the actual contribution of the rubberized mixes? Is it positive or is it negative? Then the other thing that is good to mention is that something that has been shown in previous study at the University of California Pavement Research Center, and a very recent study at Oregon by Katie Holzer of the city of Gresham in Oregon, is that the porous pavement and the open graded asphalt mixes can reduce the overall contamination of the runoff water. And in particular, the study done in Oregon, in the city of Gresham, has shown that the porous pavement can reduce the 6 ppdq contamination by at least 75%. So now we're going to show some results, some additional knowledge that we have about this topic. So please, Dr. Harvey.
Okay, thank you. And this is less knowledge than conjecture. This was a conceptual calculation of the amount of, and using what I believe are some conservative assumptions, but this is what the study that Angel is going to describe will be evaluating. Just to get a relative idea of the amount of tire rubber available for 6 ppdq release from two types of rubberized mixes and then from tire wear on the same highway. So here I've done a quick calculation looking over 20 years and assuming that's about the RHMAG typically has a design life of 20 years. So we would be replacing it and putting some fresh RHMAG every 20 years. The RHMA-O, I assumed a design life of about 15 years, and that's an average that comes out of a very large study that we did for Caltrans in 2006. So in the 20-year analysis period, I refreshed the RHMA-O at 15 years and make it available again. The rubber, I made an assumption. So the amount of rubber that's used in each of these mixes, and this is for 1 lane mile. So a mile of pavement, 1 lane wide and 2¼ inches thick. And I'm assuming that the desorption of 6 ppdq is uniform throughout that entire layer. Although, as Angel said, initially it would just be surface abrasion off the few rocks at the surface. And then if there's cracks allowing water to get in, that would increase it. Now, I made an assumption that about 1% of that rubber would be available to leach in the RHMAG, which is an impermeable mix, meaning that water is not supposed to go through it, and it doesn't. The RHMA-O, on the other hand, as Angel mentioned, is permeable. So I assumed that 10 times more of the rubber is available for desorption in that. And the RHMA-O also has a higher asphalt rubber binder content in it. So I included those calculations. I want to make a note. I just checked these. Those are metric tons. I should have spelled it TONNES to indicate metric tons. So for the 1 lane mile, over the 20 years, I calculated 0.113 metric tons available from the RHMAG and 2.071 metric tons. And this is very conceptual, so I should have just rounded those. Those are not significant digits. Okay, this gives an idea of order of magnitude. Freeze those two numbers in your mind, if you can, 0.1 and 2. And let's go to the next slide. Okay, this is a very rough calculation again, and I pulled the numbers out of the literature. In terms of, for comparison, tire rubber available from tire wear. And I looked at two cases. I looked at a low volume county road handling 1,000 vehicles per day, and I divided that in half for the one direction. And I assumed 20% trucks on that. That's pretty heavy, but that's not atypical. And I came up with 0.8 metric tons over the 20-year period. So compare that with the 0.1 for the RHMAG and the 2 for the RHMAO. Again, with relatively conservative assumptions there, somewhat conservative here, also in that the amount of trucks are major contributors of tire wear. The amount of trucks might be 5%, 10%, 15% rather than the 20% I assumed. I then took a boulevard that has 5,000 vehicles per day in the one direction. I reduced the truck number, so it's got more traffic. I assumed fewer trucks in an urban environment, 7.5% trucks, and I came up with 4 tons. So compare that with the 0.1 for the RHMAG and the 2 for the RHMAO. So this is just some very rough relative to have an idea of the rubber available from the tire wear and some conjecture about how much rubber might be available for leaching out of the asphalt mixes. As Angel mentioned, what I didn't calculate here is that open graded asphalt, as long as it remains permeable, is used as it's known, very well known and measured to slow stormwater down and capture a lot of pollutants and also reduce the intensity of the flow out of the pavement. An impermeable pavement, when it rains, the water will go straight into the receiving waters, depending on the shoulder condition and how it's getting there. With an open graded asphalt, that same pulse of pollutants will be spread over several days because of the water enters and then has to find its way through the open graded material to the side. Now, next slide, please. Here's the QR code for a study that we published in 2008. We were the pavement engineers and the principal investigators for this. Tom Young and Peter Green here at UC Davis were the environmental engineers and scientists who did all of the environmental analysis of the effluent that we captured. What we did is we took a bunch of different pavement materials. We set them up to have clean water flowing over them. And we measured and then we captured samples. And then those were taken into the UC Davis Environmental Engineering Toxicology Lab and tested for a wide range of pollutants. We included RHMAO and RHMAG in that. We also included aged, meaning that we oxidized the materials in the oven after we compacted them to simulate longer term aging to see if the longer term oxidation exposure to heat and hot air created additional chemical compounds. This is the same apparatus that's described in this report that we saved it, that will be used for the upcoming study. Next, please. So a key element of this experiment is that we ran the water through these specimens. You can see the apparatus on the left at 4 degrees Celsius, 20 degrees Celsius, and 45. So about 40 degrees Fahrenheit, 67 degrees Fahrenheit, and 115 degrees Fahrenheit. What they tested for were conventional water quality parameters, a family of nutrients, minerals, trace materials, organic constituents, and then for a subset of those materials, which included the rubberized mixes, they did some standard toxicity for some species, which we know are far less sensitive potentially than salmon and definitely to 6-ppdq. 6-ppdq was not included in this study because the potential toxicity was not known at the time. So the study Angel's going to describe is to go back and basically redo this, focusing on the rubberized mixes for 6-ppdq. Next, please. Okay, quick summary of a few of the most relevant results out of the report. No toxicity for RHMAO, and this for those three species, RHMAO and RHMAG for the 4 and 20 degree temperature water samples. Toxicity was seen in the majority of the leachate samples, resulting from all of the asphalt and the concrete conducted at 45 degrees C, as evidenced by reduction in reproductive output for most of the samples. And this data set included the RHMAG and RHMAO, and that finding is applicable to them. So this is something I think we need to think about coming out of that study. If we're dealing with rainstorms, summertime rainstorms, where the pavement is hot, and in a very hot in a hot California environment, the pavement can be at 115 Fahrenheit. That stormwater is probably our primary concern for the toxicity. And that's one thing to think about also in terms of when we get into this, and my brother is a salmon scientist, I think we're going to need to be thinking as we interpret these results, when are the salmon in the water? Does this stay in the water? And what are the exposures relative to when the salmon are in the water? So I think that's now most of our rainfall, which is in the wintertime, particularly when most of the salmon are spawning, is going to be more probably the 4 and 20 degrees results are more applicable to that. So this is just kind of very conceptual, but food for thought, I think, in terms of as we're all trying to move forward and save the coho. Next, please. Okay, I'll pass it back to Angel.
Okay, thank you. So that brings us to the third part of this presentation, which is just saying that we're going to be conducting research for CalRecycle. We really appreciate and thanks CalRecycle for this opportunity. So the research project is about to begin, has just begun actually. The period is July 2027 to June 2028. So the goal is the assessment of the risk of 6-ppdq leaching from rubberized asphalt mixes in California. And these are the main questions that we want to answer, right? The first one is, what is the risk of 6-ppd pollution from rubberized mixes? Is it real? Is it a lot? Is it very small? How does the risk depend on the type of asphalt mix? Okay, we have different type of mixes using the rubber and different binders. We want to see if that has an effect. How does the risk depend on the climate factor and asphalt mix aging? Climate factors, we know, based on the previous study, are going to be very important. And as John was mentioning, the key point is when this can be affecting the salmon, when we have the rainfall. Also, we know that the seasonal effects are very important when it comes to 6-ppd contamination. So that's a very important factor here. We want to see what is the possibility of the absorption of the 6-ppdq in the asphalt mix, because we know that based on the previous study at the University of Nevada, Reno, that may be a very important factor where we may see that the asphalt mixes do not contribute to 6-ppdq pollution, but the other way around, but they improve or reduce the contamination. And if there is any contamination, we want to put that in perspective. How much is that contamination compared to the contamination that we know is coming from the tire and road wear particles? And the approach is going to be basically the same devices that we use, the University of California Pavement Research Center used for the previous study. We will be doing laboratory control simulation of stormwater runoff on rubberized asphalt mixes. So again, we will be using the same set of apparatuses that we used for the previous study. The experimental design that we have produced consider a total of 62 run-off tests. We want to study the effect of how the contamination changes depending on the material, the type of asphalt mix, depending on the compaction level. We know that there might be big differences depending on whether what is the compaction level of the mix and whether we're dealing with porous asphalt versus dense asphalt. Want to see the effect of the mix aging. I mean, is the release the same at the beginning or after 5 years? We want to explore the different sources of pollution. Again, we have different sources of potential pollution, right? One is the asphalt binder that covers the asphalt mix right after the construction. That is going to be removed by the traffic. We want to see the actual disintegration of the asphalt mix, those particles that may be released into the water. And we want to see the leaching from the body of the mix. We know that the water will come in the mix and that will be released. So when the water is released, what is the problem? Is there more, will we find more 6 ppdq in the effluent compared to the influent, or the other way around? We want to see the effect of the temperature. We know that is very important. And the time, the seasonal variation. We know it's not the same the beginning of the rainfall season compared to the end of the rainfall season. So those are the variables that we're going to be studying in this research. Very important, we know that the quantification of the 6 ppdq is critical. It's not easy. There are very few laboratories that can provide a reliable quantification of the 6 ppdq. The analysis will be conducted at UC Davis Civil Engineering Department by Professor Tom Young. And that's a critical part, okay? Being able to measure the 6 ppdq in a reliable way. And these are the expected outcomes. And I'm going to be reading them literally. So the first one is we want to quantify the relative contribution of rubberized asphalt mixes to 6 ppdq contamination compared to the tire and road wear particles. Again, we want to know if there is any negative effect, how much that is compared to the 6 ppdq coming directly from the tire and road wear particles. We want to identify the key factors controlling this contribution. Is the rubber content? Is it the type of mix? Is it the temperature? Is it the traffic? Then, if the rubberized asphalt increases 6 ppdq concentration, if there is a negative effect, we want to evaluate potential mix-related mitigation strategies, okay, in case the contribution is negative. In case the contribution is positive, because that's another possibility, that the asphalt mixes will be absorbing more 6 ppdq than contributing, then we want to consider the asphalt mix also as an opportunity to reduce the environmental impact of the 6 ppdq. So this is the main conclusions. And again, I'm going to be reading them. The first one is that the preliminary laboratory results suggest that the contribution of rubberized asphalt mixes to the 6 ppdq contamination in California is likely negligible and it may even be beneficial. Okay, again, preliminary laboratory results. Then, but given the ecological significance of 6 ppdq and the widespread use of rubberized asphalt in California, a rigorous scientific assessment is needed to quantify its contribution to 6 ppdq contamination. Again, we believe that the concern is reasonable, and that's why we believe that doing research is necessary. And then the research that we're going to be conducting for CalRecycle is designed to address this knowledge gap. Again, the research will be finished by summer 2020. So that's it.
Angel, one thing I would add is that in the same apparatus, we're going to be testing loose tire particles, and that's going to be our baseline comparison so that we're using the same methodology for the leaching.
Okay. So Mustafa, back to you. Thank you very much, everybody, for the attention.
Thank you so much, John and Angel, for that great presentation. And with that, we will now start the question and answer portion of the session. If you haven't already submitted, please submit your questions in the Q&A widget. And if your question is specific to a presenter, please include their name at the beginning of your question. With that, I'll hand it to Kevin, who will, ask the questions. Go ahead, Kevin.
Yes, thank you very much, Moose. Do want to take some time to recognize there was a system issue with Zoom. and that there was a problem with some of the registrants had from accessing this session. I just wanted to notify that this session will be recorded, and CalRecycle highly recommends that after watching this session, please reach out if you have any unanswered questions, as CalRecycle will be happy to answer them. With that, we will get started. And our first question I would like to direct to Dr. Eileen Cashman. You noted that zinc, iron, and manganese are the main metals that leach from TDA. Are there specific site conditions, such as proximity to a sensitive waterway or a low pH environment, where you'd recommend against using TDA altogether based on current evidence?
Thank you, Kevin. If I may, I could pass this question over to Brad Finney so he could chime in on that. If Brad, if you're there and available. Maybe not. Maybe he's not there. Yeah, well, I'll start, and Brad, if you can chime in, go ahead. The main concern with metals and leaching is the pH of the water that's in contact with it. So, as we mentioned, many of the applications for tire-derived aggregate installations are in contact with waters that are close to neutral anyway. That's what urban stormwater's at. And so applications that would be inappropriate would be places that have really low pHs where you might see higher metal leaching. So acid mine drainage treatment or something of that nature. Did I answer that question? I think I.
Yes, that sounds good. Thank you very much for your answer. Next, let's see. I have a question here for Dr. Kelly Grant. Can you discuss the fate of 6-PPDQ?
Sure, thanks. That's a great question and a somewhat difficult one. I think when 6-PPD and 6-PPD quinone were really first looked at, folks thought they were pretty transient in the environment. And it's true that 6-PPD quinone does diminish from the water column quite quickly, but we've seen it, several studies have found it in relatively distant from sources. The San Francisco Estuary Institute has actually found 6-PPD quinone in the water of the bay. Studies in China have shown 6-PPD quinone does go out into marine environments. So I think it might last a little bit longer than we initially thought. And then it does get sorbed to sediment as well. So there might be a concern for animals that live in the sediment as well.
Great. Thank you very much, Dr. Grant. Is there anything anyone would like to add? If not, we can move on. There's a question for Dr. Angel and Dr. John Harvey. Can asphalt encapsulate ground tire rubber and 6-PPD?
You want to go, John?
Sure. Yeah. And I answered that in the written. So the rubber particles and the powdery part as well. So the very biggest are 2 millimeters, and it goes down to smaller than that, 75 microns. Those get reacted at high temperature with the asphalt binder. The asphalt binder, during that reaction, some of the bigger particles actually exfoliate and become a part of the asphalt. And the rest of the particles, the larger particles, and most of the smaller particles do the same. They are completely blended. Some of the larger particles don't completely exfoliate, and so they're embedded in that asphalt binder. And asphalt binder is a sealant. I think the asphalt binder gets softer, and just everything becomes more reactive as it gets hotter. So I believe it encapsulates it. particularly at colder temperatures. At higher temperatures, things may come out of the asphalt to some degree. That's what we saw in the previous study at 115 degrees Fahrenheit. Chemicals work and other substances were coming out of the asphalt mixes, and actually out of concrete as well. All our pavement materials. So yeah, I think it's contextual, but it does do a lot of encapsulation.
If you may me add, uh, based on the data that I have seen today for the first time, I think it was Dr. Cashman, she was presenting the 6 ppdq release from tire-derived aggregate with this no encapsulation. If we compare that versus the data that was published by the University of Nevada, Reno, it seems that there has to be encapsulation because the release is two orders of magnitude lower from the asphalt mix compared to the actual rubber. So there has to be.
Yes, that makes sense. And thank you both for the detailed
Can
answer.
I make a comment if
You
possible?
can, Brad. Yes, go ahead.
Yeah, one of the things I think that needs to be explored, and maybe your study can do that when you're over the next couple of years, is 6 ppdq or 6 ppd migrates through the rubber. So independent, I mean, it was designed as that's part of the process, how it protects the tire. So the fact that it's migrating through the rubber, my question would be, is it also migrating through the binder
Yeah,
and through
that's a
the
question.
asphalt mix? And I don't think anybody really knows that right now. We looked at similar kinds of leaching studies ourselves, but focused, unfortunately, at the time only on metals. And we didn't see a lot of if you would want to call it migration. So you get a sense of the fraction of the zinc contained within the rubber within a cube of asphalt, rubberized asphalt, how much of that could potentially leach out. We'd let it sit a year and find out, but no one's done anything like that for 6 ppd and 6 ppdq. So that it would be interesting if you could simultaneously in your study just take a slab of asphalt that you have some sense of how much is in there in the first place, throw it in water and let it sit a year as your study goes on and see what happens.
We're planning on doing that.
Yeah, that's
Okay,
part of the
great.
study. Yeah,
Great.
And again, Brad,
good suggestion.
if we can, any input regarding the experimental design that we have created, it could be really appreciated.
I have to note, Brad, I was your student in January 1989. I haven't seen you since then, but
Yeah, we've both gotten a little older.
just a little.
Yeah, well, that's awesome, guys. Thank you all. Thank you for that great conversation. We have time for one more question. This question is for Dr. Kelly Grant. What is the leading idea of why 6 ppd is acutely lethal to some types of fish and not other types of fish?
Again, really great question. I wish we knew. We just don't know. What we do know happens is that the blood-brain barrier and the blood vessels of coho become very porous and they start to leak. So fluid gets into the brain, fluid leaves the blood out of the gills. We don't know why. There's a lot of research trying to understand that and trying to understand why it's so species specific, but we just don't know yet.
Thank you, Dr. Grant. We're going to leave the Q&A open for another few minutes since we have the technical issues with people joining. I appreciate you guys all being available. I'll ask a couple more questions. The next question, since Dr. Brad Finney has joined us, I'll address this to Dr. Cashman and Dr. Finney. You found that TDA actively removes phosphorus and nitrogen. Has there been any serious discussion of intentionally designing TDA in stormwater or wastewater treatment systems specifically for nutrient removal rather than just as a structural fill?
As Eileen pointed out, one of the issues of concern, perhaps, with using TDA as a nutrient removal mechanism is that process primarily is dependent upon having the iron associated with the wires in the tire. And there's some concern that over time, as the iron is sort of used up and it basically rust out, oxidize out, that you'll have a loss of effectiveness. There is up in the San Juan Islands, there is a community that has a wastewater treatment facility that has a constructed wetland that used TDA as their fill material. And I saw that on Lopez Island. I went to the facility. It had been in operation over 10 years, and the amount of iron still coming out of that basin was I mean, I couldn't believe that it survived all that time. So I actually, just from that one anecdotal experience, I think that it probably more effective over a longer term than perhaps we're concerned about, but no one's done that test. There have been some designs proposed. Joaquin Wright and Joaquin Wright, who works for GHD, and I actually proposed a design that would have looked at nutrient removal from stormwater. That particular design has not been implemented, but there at least has been some work in terms of looking at that, but no process that I know, no real installation that's in place has specifically been implemented for that purpose.
Yes, thank you, Dr. Finney. The next question I will pose to Angel and Dr. Harvey. It says, "Thank you for your response. When you said in your presentation that the effect of 6-PPD is not only bad in asphalt mix, but it also helps with mixed property, what kinds of property is it?"
So it's the 6-PPDQ is not what improves the cracking resistance of the asphalt. It's the rubber itself. 6-PPDQ, we didn't even know it was in there. It's not something that we're looking for. It's not why we're using the rubber. The asphalt rubber does two things. At high temperatures, when we're mixing and then placing the asphalt, it helps hold the asphalt up in the mix so we can use a higher binder content. We also find that the rubber itself in bending is helping us with the cracking resistance and also with age-related cracking, meaning that as asphalt gets old, it gets oxidized. It can't handle contraction when on a cold night without cracking. So that's how the rubber is helping us. We didn't even know 6-PPDQ was in there. Never heard of it until 2 years ago.
Mm-hmm. Thank you, Dr. Harvey. Let's wrap this Q&A session up with the last question for Dr. Kelly Grant. We'll put Kelly Grant on my spot. What happens in the SCP regulatory process if industry does not find feasible alternatives to replace 6-PPD in tires?
Thanks for that question. One of the reasons we did push back the timeline for the final alternatives analysis is to really try to allow time for innovation to occur. So we are still hopeful that it will, but in case it does not, there are regulatory responses that we can implement that would require manufacturers to invest more in research and development to look for safer alternatives. So that would probably be the best path for that hopefully non-eventuality. Hopefully we get to a safer alternative, but just in case, we do have that option.
Thank you very much, Dr. Grant. That will conclude our Q&A session. I want to thank you all for your time. Now I will pass it back to Moose.
Thank you, Kevin. And I just want to take the opportunity to thank the panel or the presenters, Eileen, Brad, Kelly, John, and Hal, for the great presentation and the discussion this morning. As a reminder to the audience, all the presentations are available on the conference agenda webpage. So this marks the end of this morning session. Thank you all for joining us. The presentations were really insightful, and we appreciate you being here. Stick around for the next session at 10:30. And with that, I will hand it over to Tommy. Back to you, Tommy.
Thank you, guys. Thank you again to our panel. As Moose said, we appreciate it. And I already put it in chat, but again, we apologize for folks who were not able to get in the webinar, and thank the people who were able to come in early and be able to watch the entire session. Thank you for the questions that you offered. Good news is the link has been fixed. It is the same link for all the webinars and be the same one for the 10:30 session. So again, thank you guys for joining. We're going to step away just for a couple minutes. I'm going to close out the webinar so we can clear out our current panel and then start our next session. And just as a reminder, the next session is our final one from 10:30 until noon. We'll be opening up the webinar about 10:25. Our last workshop name is Program Funding and Grants, Accelerating Progress in Tire Recycling. So we hope that if attending this session, that you will also be able to come back in and attend that next session on there. With that said, we're on our virtual stretch break. Again, I want to thank Moose, Kevin, Kyle, Eileen, Brad, Kelly, John, and Hill for your presentations today and having the great conversations. And again, thank you for being on this panel. As Moose said, presentations for each of these presenters today is currently posted on the session description page. You see it there. And then, like I said, to reiterate, the recording will be available at a later date. Once that's on CalRecycle's YouTube page, we will get that posted there. Also posted on the agenda page so that you guys can go back in and look at the session. So with that, I'm going to go ahead and end this session. Thank you.